Dear students, welcome to the lecture series of Digital Electronics, Digital Fundamental. We already discussed the simplification of Boolean function using the Carnot method for sum of product or product of sum, as well as up to the 5 variable and don't care condition. Now, the next step after the simplification of Boolean function, the implementation. And in digital circuit are more frequently constructed with the NAND or NOR gate than with AND and OR gates. First reason is that the NAND and NOR gates are easier to fabricate with the electronic components and are the basic gates used in all IC digital logic families. Because the prominence of the NAND and NOR gates in the design of digital circuits, rules and procedure have been developed for the conversions from Boolean function given in terms of AND, OR and NOT into equivalent NAND and NOR logic diagram. This means we can implement any function with the help of NAND and NOR gate. So NAND and NOR gate are also known as a universal gate. Today we will discuss the procedure for two-level implementation, and multi-level implementation is also possible, which we will discuss later on. But to facilitate the conversion of NAND and NOR logic, it is convenient to define the other graphical symbols of the gates which are normally required. So let us start with the things. As we know that we start with the before that things, we discuss how the simplification two-level circuits are possible. Like is here, the function is given that the sum of min terms 0, 1, 2, 5, 8, 9 and 10. So we put here 0, 1, 2, 5, 8, 9, 10, and as we make it, the outer cell or corner cells are B dash D dash, and the second possibility that the first two cell of upper row and lower row is B dash C dash, and the green combination is that A dash C dash D dash. So the equation will become function is equal to B dash D dash plus B dash C dash plus A dash C dash D dash, and this is called as a sum of the product term. Three product terms are there, where two products are based on two variable, while the third is depends on the three variable function. In total, four variables are there: A, B, C, D. So this is the diagram with the help of also product is done by AND operator. So here the first B dash D dash is AND gate. So output of the gate number 1 is B dash D dash. The output of gate number 2 is B dash and then C dash, and the output of gate number 3 is A dash, second is C dash and D. So in this way, and after that OR gate is that all three functions are odd. So we put here OR. This is known as a AND OR level implementation. Okay, two level, one is the AND level and second one is OR level. This is normal practice in sum of product. Product is done by AND gate first level, and all the output of the AND gate is ORed with OR gate. It is known as the AND OR level implementation for sum of product simplification. Let's take, so the same thing is that if we take the complement, so remaining all the min terms are replaced by 0. Okay, now we simplified it. So this will become both are 1 1 A B. So it is like as A dash plus B dash. So outer these two green is so that BD equal to 1 0 means B dash plus D, and the red is C and D both are equal to 1 1, so it will become C dash D dash. So we can say that the function is in product of sum is A dash plus B, C dash plus D dash and B dash plus D. So in this way we can also identify the duality. Function is given in product of sum term. So product of sum. So sum is that. So first we take A dash plus B, second OR gate is C dash D dash, and third OR gate is B dash D D. So 1, 2, and 3 functions are there, and then all output of these three functions is ANDed. So product of sum is implemented by OR AND level implementation. Whenever our function is in terms of product of sum, first level is always OR gate, and the output of each and every OR gate is ANDed with second level AND gate. So OR AND logic is normally useful for product of sum. Now, NAND implementation. So to facilitate the conversion to NAND and NOR logic, we have to find out it is equivalent. So two graphical symbol, this is the NAND gate. Suppose X, Y, Z, three inputs are there. So output F is equal to X, Y, Z whole dash. Now, this can be look like as invert OR. First, this bubble so that whatever the X, the input is X dash, Y is Y dash, and Z is Z dash. So F equal to X dash or Y dash or Z dash OR gate. But the input is complement because the bubble is come before the input of OR gate. Okay. X dash plus Y dash plus Z dash. As per the De Morgan's theorem, is expansion of X, Y, Z whole dash. Because when I expand this thing, it will become X dash and replaced by OR, Y dash and replaced by OR and Z dash. So this is known as a, the output is result equal to same NAND gate, but it is known as a invert OR NAND equal to NAND gate. Similarly, suppose there is an inverter. As we know that the inverter output is always complement of the input. If input is 0, output is 1, and if input is 1, output is 0. The same thing is possible if in NAND gate only one input is there. So F equal to X dash and invert. It is called as a AND invert. So NOT gate is replaced by AND invert gate. Let's see. Suppose three ways to implement. As we already discussed that sum of product. So sum of product first level is AND gate and the last level is OR gate. Like is it this way. AB plus CD plus E. AB is the first AND gate output. CD is the second gate in output. And this all three are OR. So this two level circuit is known as a AND OR implementation. Now this AND gate, if I want to replace these two AND gate by NAND gate, so bubble will become here. Okay, now if here if F I replace by F dash like in this way, what happens? I have to put the invert here. Then both the circuit remains same. A B whole dash. The output of the gate one is A B whole dash. But A B whole dash is a first invert and then A B. CD whole dash. But CD whole dash will become CD due to this bubble. So it will become CD. And E dash, remember that thing. Here we replace E replaced by E dash. So E dash is input bubble, it will become E. So F equal to AB plus CD plus E. Why we put this thing? Because now you can see here, this is look like as an invert OR. So we can replace this F gate or gate or invert OR gate by NAND gate like in this way. So whole function like is AB whole dash here, CD whole dash here, E replaced by E dash, so E dash whole dash, it will become dash dash De Morgan's theorem AB dash dash AB. NOT gate is replaced by AND gate, CD dash dash CD, E dash dash equal to E. Here E dash is that, sorry, it is by typing mistake, E dash is here. So with the help of NAND gate, we can implement the circuits. Remember that thing, the digital components are always available in integrated circuit. So one in ICs have a 4 or 5 NAND gate, and every IC have a different gates. So here multiple ICs required because the inverter NAND and OR gate is there. While if I replace whole the circuit by one type of gate, the circuit size is reduced. So as we here saw that the AND invert symbol has been previously consist of the AND logic. So small circuit, small circle of NAND gate, and here in this way we can give the original, and this is replaced by NAND gate. Same thing is also possible with the help of NOR gate. Suppose the function is given here 0, 6. So what we will do, f equal to, okay, here the one example how they make the NAND gate 06. So function 06, this one, x dash, y dash, z dash, x, y, z whole dash. So the first is NAND gate x dash, y dash, z dash, x, y, z dash, and these both are given into the second NAND gate f equal to this function. So sum of product directly we can convert into the form of NAND gate. Okay, remember that thing. And second possibility is that if we take the f dash is x dash y, means this one, x is equal to 0 and y, these two minterms is x dash y, x y dash is these two minterms. Okay, x and y dash, y is equal to 0, and middle 4 is z, so this z is there, so f dash is that, means x dash y, in the first NAND gate, x y dash here and z, and it is given to here. So my this will become f dash, but I want to convert f, there is require one another inverter gate is there. Okay, so if I take the zeros and take f dash, it will become 3-layer circuit, 1 layer, 2 layer, and 3 layer. While if I take f, it will become 2-layer circuit. So function in sum of product 2-level NAND gates. Remember that thing. Function in sum of product 2-level NAND gates, while f dash function in sum of product. If f is there, so left hand side yellow part is that, but if the function is given in f dash is given in sum of product, the level of gate will become increased by 1, and as level is increased, the time taken by to generate the f will take more time. 2 level, so 2 delay is there. 3 level, so 3 times is required to generate the f. So this is 3 level NAND gate if f dash is given in sum of product. Right? Note down that things. There's a big difference. If f is given in sum of product, there is equal 2 level NAND gate. But if f dash is given in SOP form, there is equal 3 level NAND gate. Now the second thing is that the NOR implementation. The implementation of Boolean function with the NAND gates require that the function to be simplified in SOP form. To see the relation between the sum of product expression and its equivalent to NAND implementation. Okay. Now, for NOR gate, the output is x plus y plus z whole dash. Again, if this will become replaced, invert AND. Okay, here invert AND. So first whatever the variable x, y and z inverted, so it will become x dash, y dash, z dash. And AND gate is f equal to x dash into y dash into z dash. And this is the expansion form of x plus y plus z whole dash. As per the De Morgan's theorem, we can say that. So this the functionality of this type of the gate is NOR gate. And it is known as a, first we are inverting then ending. So invert AND is equal to NOR gate. Similarly, for inverter x dash, so if I give one input in NOR gate, it is behave like as a or invert x dash f equal to. Suppose that there is a three-way. Now same thing is there, but it is in product of sum a plus b, c plus d, and e. So simple thing is that OR gate a plus b, c plus d second OR gate, e, and function is product of sum like is in this way. Now this NOR gate is replaced, so it will become complement here. I have to complement here. So two bubbles are required, 1 and 2. So finally, whatever the output of our OR gate, it is ended with the other one. Okay, like as here bubble and here bubble. So meaning is same. The circuit is not changed here, but this bubble is replaced by E dash. So we got it. This is look like as a NOR gate. So I can replace this now by NOR gate in this way. So my function will become AB whole dash, E plus B whole dash, C plus D whole dash, E dash, E whole dash, E dash this whole dash. So A plus B ended with C plus D and ended with this. So it is known as a product of sum by two level NOR circuit. Suppose the function is given 0 and 6. As we discussed previous, so first we have to find out in product of sum. So f dash is equal to, as we already defined, x dash y, this one, these two OR gate, X, Y dash, these two are gate, and combination of middle one is Z. So what we'll do, F equal to F dash is this, so F equal to X dash Y plus X Y dash Z whole dash complement of the this one. So it will become converted into the product of sum X Y dash ended with X dash plus Y ended with Z dash. Okay, in this way, two level NOR circuit is that. The first level we generate X plus Y dash inverted, X dash plus Y dash inverted, Z dash inverted, and then again it is NORing and inverted, it will become X plus Y dash and then X dash Y plus Z dash. So if F dash, we take the F dash. For that, first we take the F. F is equal to this and this. So F dash is equal to X plus Y plus Z and then X dash Y dash Z. Okay, this is also product of sum term. But here, first we find out the F dash and then inverted by NOR gate. So this is the 3-level NOR gate circuit, while the first case is 2-level. So 2-level is only possible when the function is given in product of sum. If F is given in product of sum, 2-level NOR gates are required. But if F dash is given in product of sum, F dash is in product of sum, there is required 1, 2 and 3-level NOR circuit. One additional NOR gate is required to complement F dash into F. Okay, so the conclusion of this thing is that the rules for implementation NAND and NOR gate is that first, if the function is simplified in F form with the sum of product, so we have to combine all ones and 2-level NAND circuit is generated like in this way. Okay, NAND gate this way. F function of some term 2-level, F dash is SOP 3-level NAND gate is there. Okay, if F dash, so it will become 3-level NAND gate. We have to combine all zeros because we have to find out F dash. Combine all zeros min terms and find out the sum of product F dash. It will become 3 NAND gate is there. While in NOR gate, F is in product of sum. So NOR gate combined F dash. How F dash is we have to do? Which one? F dash. So complement of F dash is given. F is in product of sum. 2-level NOR gate is there. Like in this way. F dash, first we compare F dash, complement it. So function is in POS form and 2-level. But if F is in min terms form, F dash in product of sum. If F dash in product of sum, there is required 3-level NOR gate circuit. Okay, so this is very important parameter. Our F is in which form? Sum of product. So 2-level NAND gate is required. If F is in product of sum, NOR gate 2-level. But if F dash is in SOP form, 3 NAND gate level is required. And if F dash is in POS form, 3-level NOR gate is required. So I hope is it making sense that how the NAND and NOR implementation is required. Remember that thing. From the transformation, we conclude that the Boolean function can be implemented 2 levels NAND gate. The rules is obtaining the NAND logic diagram. First, we simplify the function in SOP form, this one. Then draw the NAND gate for each product term and at least 2 literals. The input NAND gate are given to the second level. Draw a single NAND gate which is inverted or graphic symbol to the second level and combine it. So it require only 2 NAND gate logic. Same for NOR gate. While if we take a F dash, there is 3 level because we have to combine zeros in SOP form and 3-level NAND is there. While in POS form, we complement if in terms of POS, so F dash is required 3-level NOR gate circuit is there. So this is the summarized procedure for NAND and NOR implementation. Well, one should not forget to always simplify the function in order to reduce the number of gates in the implementation. The standard forms obtained from the map simplification procedure apply directly and are very useful when dealing with the NAND and NOR logic. I hope is it making sense and it will be helpful to you for the implementation of 2-level NAND and NOR implementation circuit. Have a good day.